So hello everyone, I'm Nairen. I'm going to talk about the correlation clustering in the sequential setting. Our paper is Understanding the Cluster Linear Program for Correlation Cluster. So this is a joint work with Vincent, Yuyong, Shi, Alantha, and Lucas. So first of all, what is correlation clustering problem? In this problem, we are given a complete graph, and each edge is either positive or negative. So in the right example graph, we use blue edge to represent the positive edge. We usually only show the positive edge here, so ignore the red edge in the graph. And then the goal of this problem is to partition the graph such that minimize the disagreement. So the disagreement are the negative edge that are in the same cluster or the positive edge in the different cluster. So here in this example graph, we have 4 partitions. And for the negative disagreement, we have KL. For the positive disagreement, we have DK, this CO, and CF. The disagreement is 4 for this example. So this problem is an NP hard problem, and people even show it's APX hard problem. So we can only target for some approximate ratio. There are a lot of work trying to improve this approximate ratio, and until very recently, people get 1.73 approximate ratio. To get the better than 3 approximate ratio, people usually use the following framework. They devise an LP, and then we first solve the LP, and then given the fractional LP solution, we then round LP to an integer solution. One of the most common used LP we use is this metric LP. So we have XUV for each edge here. XUV is the distance between two nodes. So if it's 0, that means their distance are very close and they should be in the same cluster. And then we have the first constraint is the triangle constraint. That's the reason why we call it metric LP. And we have the objective, which is minimize the disagreement here. However, for this metric LP, there is an integer gap here. So if you consider the example graph, which is on the right side, this is the star graph. The center is C, and there are a lot of other nodes here. For the OPT, so we simply cluster one of the node with its center. So it's CF here, and put all other nodes in a singleton here. So the OPT is n-1. And then for the LP value, if we set all the positive edge as half and all negative edge as 1, then the triangle inequality will be satisfied. And the LP value for this is half n. So you can see that there is an integer gap of 2. So if you want to get some better than 2 approximate ratio, you have to do something more for this problem. So to get better than 2 approximate ratio, we have to enhance the LP. Actually, there are already some results. People already consider the Shirley-Eden hierarchy, and by using this hierarchy, they get a better approximate ratio, and it's a very recent result. It gets 1.73 approximate ratio here. So once we have this LP background, now we can talk about our result. So we have 4 results here. First, we proposed another LP, which we call cluster LP. This LP unifies all previous LP. And then we show that our LP can be solved in polynomial time. And thirdly, once we solve our cluster LP, we devise a rounding algorithm. This gives us a better upper bound for the correlation clustering problem. And at the end, we also give some lower bound for our cluster LP and the correlation clustering problem itself. So this is a graph for our result here. On the left side is our cluster LP, which we devise. And then on the right side, so we first solve the LP in polynomial time, and then we round our fractional LP to an integer solution with a better upper bound. And in the middle side are the 2 lower bounds. One is for our integer gap of the cluster LP, and the other is for the correlation clustering itself. Now we are going to talk about our results one by one in more detail here. So first is cluster LP. Cluster LP is an exponential size LP. It's a very natural LP here. So we have the S variable for each subset S. The S equals to 1 implies that S should be put in one cluster. So the first constraint means that each node should be only put in one cluster here. Then for the second constraint, recall that xuv is the distance for uv. So 1 minus xuv is the probability we should put uv in the same cluster. So this equals to the summation of all s for those s containing u and v. And the objective is simply the disagreement here. So secondly, since this is an exponential size LP, so it's not that easy to solve it directly. And in our paper, we show that we can solve it within 1 plus epsilon approximate ratio for this cluster LP and runs in polynomial time. But this polynomial also depends on 1 over epsilon, so it's not that good for us. So once we solve our cluster LP very well, then we also give a rounding algorithm that outputs a cluster within 1.437 approximate ratio in the paper. So combining with the result of the solving cluster LP, so our main contribution is there exists a 1.437 approximate algorithm for correlation clustering, and it runs in polynomial time. At the end, we also give two lower bounds for this problem. So the first is the integer gap for the cluster LP. We show that for cluster LP, the integer gap is at least 4/3 here. And then we also give a NP hardness reduction for obtaining an algorithm within an approximate ratio of 24/23. However, our reduction is a randomizer reduction. It's not a deterministic reduction. But this is still the best possible NP hard result we can get now. And in the remaining of this talk, I will talk about some detail people care about. Because of the time, I will ignore the lower bound part and mainly focus on solving the cluster LP and the rounding algorithm. So for the solving LP part, I will mainly talk about the difficulty, but leave the reader for the detail. And then for the rounding algorithm, I will give you some high-level idea why this rounding algorithm works for our cluster LP here. So our cluster LP is an exponential size cluster LP. So one may think, can we use considering its dual? We already know that ellipsoid algorithm can solve this exponential size algorithm, can solve exponential size linear programming here. Unfortunately, the answer is no. That's because if you write down the dual of this cluster LP, is on the left side, we will have a weight for each pair of nodes, HUV. And then the first constraint is saying that for each subset, we want the total edge weight in this clique is at most 0. And the second and the third constraint is to say that the weight of the edge cannot be arbitrary. So if we want the ellipsoid algorithm works, we want an oracle which can return us a violated constraint. That means we want an oracle that find an S such that the summation of all edge weights in this clique should be greater or equal than 0. So basically, you want to find a clique whose edge weight is satisfying some condition here. So it's not hard to see. It's not hard to see if you write this down. We can reduce this problem to the clique problem, and this problem is NP hard problem. That means we are not able to give this oracle. So that's the main difficulty if we use this standard LP method here. So in our algorithm, instead of considering its dual, we consider it's on the primal. And our algorithm actually resembles previous method here. It contains also something new here, but we also contains previous pre-clustering and the RT rounding method. Because of the time, so I will ignore the detail of how we solve the cluster LP here. So the second part I want to mention is about our rounding algorithm here. I want to give you some intuition why this rounding works. So first of all, let's take a look at this cluster LP. One very natural way is that we can explain this CS as the probability of S being a cluster. So in this talk, let's focus only on positive edge. This will make this thing more intuitively. So if we explain the S as a probability of S, what we can do? We can do the following. First, we will randomly choose a set S with this probability proportional to its value. So in this example graph, we have some nodes which has already been clustered. So the green nodes are the cluster node, which is D, contains D. And then this round, we choose a set S, which is DCE. And second, we will include all unclustered nodes in S. And for those nodes in S that has been clustered, we will not include into cluster. So in this example graph, DCE is a chosen set, but D is already been clustered, so we will cluster C and E. And at the end, we will remove the cluster node and repeat the above process. And this algorithm is not complicated. The real problem is, what's the cost for this algorithm? How much do we need to pay for a positive edge here? So if you focus on a positive edge, let's consider in the example CE. When does CE get separated here? So CE will get separated if we choose some set S such that S intersects with CE exactly one of the CE. So in this example, if we choose DCF, then C and F will be clustered and E will be put in another cluster. So C and E will be in different cluster, and we have to pay for this positive edge. On the other side, if we choose a set S which intersects both C and E, in this case C and E are in the same cluster, so we don't have to pay for this C and E edge. So if we transfer this intuition to some formula, we will get the following formula. A positive edge will separate it with probability ZS, which ZS is over all S that intersects exactly one point of U and V over those CS which intersects both 1 and 2. If you express this term and translate to some formula related to XUV, we will get this 2 over 1 plus XUV times XUV term here. So you can see that in the LP we have XUV, and in this scheme we have to pay this amount of cost for the for XUV. So the approximate ratio is 2 over 1 plus XUV. The approximate ratio is less than 2. When XUV is very small, the approximate ratio is close to 2. When it's large, the approximate ratio is close to 1. Recall that we want something better than 1.43, so we still need to come up with some idea to fix the small XUV case. So that leads to our second rounding algorithm, which is a p-weight based rounding algorithm. So basically, in the p-weight algorithm, we randomly choose the unclustered node as a p-weight. So in the example graph, green nodes are the cluster node, and we choose D as a p-weight at this round. And then the second step is the p-weight step. We will choose some neighborhood to its neighbor. So what we do is we will randomly choose a set S containing U with probability ZS. Recall that the S containing U, the summation of this ZS equal to 1, so this probability is well defined. And then we will include all positive neighbors in S to use neighbor. So in this example graph, we choose DC, and then we find C is its neighbor, so we will include C to its cluster. However, we still not fix the case that XUV is very small. So to fix this case, we have our third step. For those very small XUV positive edge, we will include it directly. So we choose this threshold as 1/3 in our paper. So in this example, we find the XUV for DE edge is very small, then we will include E into its cluster directly. So at the end, we will find that DCE is in one cluster in this round, and we will remove all the nodes which has been clustered and repeat the above process again and again until all the nodes has been clustered. This algorithm is a pivot algorithm and is not complicated neither. The real problem is what's the cost for this algorithm here? So here we use a very standard triangle analysis for this pivot-based rounding algorithm. This triangle analysis is used in a lot of previous algorithms if they also design some pivot-based rounding algorithm here. I'm not going to talk about the detail of pivot, but the high-level idea of this triangle analysis is we will assign a LP budget fxuv for each edge, and then the goal is we want to find as small as possible fxuv such that for each triangle, the algorithm cost can be covered by this LP cost. Notice that this is for each triangle, not the whole algorithm. If we can show this goal, then we can show the whole algorithm can be bounded by the LP budget here. And what we show in our paper is we assign fxuv to this 6xuv over 1 plus xuv times xuv in our paper. We find if we set to this value, then the algorithm cost is covered by the LP cost. Remember that for the set-based rounding, we have positive edge cost, which is 2 over this 1 plus xuv times xuv. If we choose the better of these two algorithms, notice that the better is always better than a linear combination of these two algorithms. Here we choose a linear combination of 1/4 and 3/4. So if we choose 1/4 for the pivot and 3/4 for the cluster set-based rounding, then we will get exactly 1.5 times of the xuv for each edge here. That means the better algorithm will always promise the returning cluster is at most 1.5 of the optimal algorithm. A natural question is, can we do better than 1.5? One may think that if we choose some smaller fxuv, then we can get some better approximation. However, this xuv is chosen after we balance positive and negative edge. What do we mean by chosen? Basically, that means if there exists a bad triangle such that the algorithm's cost exactly equals to the linear program budget if we set fxuv to this value, and the bad triangle is on the right side. It's a positive negative triangle with positive edge with xuv value half and negative edge xuv with 1. For this type of bad triangle, the algorithm cost exactly equals to linear programming budget. If we choose a smaller this budget, and then what happens? The algorithm cost is no longer can be covered by the linear program cost. So we still have some good news. For all other type of triangles, we can use smaller budget function. So for example, in a graph, if there doesn't exist any bad triangle, actually we can use smaller budget function, and this will give us a better approximation. And even if there are some bad triangle, as long as not all triangles are not bad triangle, we still have some space to do some improvement. But if all triangles are the bad triangle, then basically this is the optimal we can do. So the question now is, can all triangles be bad triangles? So fortunately, the answer is no. Because of the following this right side example, we have 4 nodes in this example. Between PU, PV, and PW, they are positive edge and they have LP value half. And between UV and VW, they are negative edge and they have LP value 1. Notice that PUV, PVW are both bad triangles. Our question is, can PUW also be bad triangle here? The answer is no. That's because you can think X as a probability of 2 nodes get separated. If XUV equal to 1, that means UV, UVW, and UW both should be separated. So they should be in different cluster. That means the events PU and PV or PW, that they are in the same cluster, these 3 events are mutually exclusive. However, notice that since we have the distance of PU, PV, and PW both are half, that means the probability that PU, PV, PW get clustered in the same cluster is probability half. That means it's impossible that these 3 events to be mutually inclusive. So XUV has to be less than 1. PU and PUW is not a bad triangle here. So based on this observation that not all triangles can be bad triangle. Actually, previous paper already gave a global charging scheme. So their idea is they divide x value into 3 different intervals, and for each triangle, so they will they will put it in one category based on this interval here. We use the same idea here, and since there are 3 intervals, so by roughly analyzing about 20 different type of triangles, then we show that we can use a smaller budget function here, and this will give us an approximate ratio of 1.79 here. And so we can extend this idea a little bit. So we will divide x value into 50 different intervals. So those triangles that are within the same interval are the same type. And then for for the triangle that are the same type, we will impose some constraint on those triangles. The bottleneck of this method is that we have too many type of triangle. Roughly speaking, we have 20k different triangle. So it's impossible that we do a hand by hand proof. We have to use the computer to show a smaller budget function. And actually, thanks for the computer, we do write down a program, and we show that a smaller budget function is possible, and this gives us an approximate ratio of 1.437. So in conclusion, we show that there exists an algorithm which can give us 1.43 approximate ratio and runs in polynomial time. So I will end this talk by some open problem. First, our cluster LP is solved in time n to 1 over epsilon. So the n to 1 over epsilon term is in the exponential set of n. Can we remove this term here? So can we solve it in time, for example, poly 1 over epsilon times n to 100? And second, notice that lower bound for the cluster LP is 4/3, and our current upper bound is 1.43. So is it possible that we give a tight bound of this cluster LP? That's it. Thank you.